booklet, which should appear soon. I must admit that the motivation we had was not to do with filtering in the normal sense, which most people think of it. In fact, I don't know too much about filtering in the classical sense. What we were interested in, our motivation, was to look at the situation where you have a space, a map P, which is going to be as smooth as you want. I'm going to not worry about analytical details at all in this talk. Where we have a diffusion operator here and a diffusion operator here, which are intertwined by P. So that what we have is that if we look at B of F composed with P, for F from here to R, then this should be equal to A of F composed with P for a sufficiently smooth F. So that's just that basic intertwining relationship between two diffusion operators. So, of course, diffusion operator, I mean second order semi-elliptic operator. So AF at X, for example, will be sigma AIJX, ij equals 1, this is on Rn, d2f by dxi dxj plus sigma bix df by dxi. Such an operator has a symbol, which I'll write here. Symbol A at a point x goes from the dual space, to be precise, for each x belonging to Rn, and it's given by sigma A x acting on a vector A1 up to AN in here, has ith component, which will be sigma AIJ. This better not be A, had it? AIJ alpha j, j equals 1 to n. So that's, these are, of course, all evaluated at x. And the semi-ellipticity means that the symbol is positively semi-definite for all x, which equivalently means that the matrix Aijx is always positive semi-definite. So I'm allowing degeneracies. That's quite important. Although, of course, the elliptic case is the usual one. To allow degeneracies, I'll also set E of x equal to the image of the symbol. So that's contained inside Rn. It's a linear subspace. If we put the two operators together, we have the symbol of B for point U upstairs going to Rk. We have the symbol of A, Rn star, at P of U. Now that goes into E of U, E of P of U, contained in Rn. We have the derivative of P, the linearization of P. So P's an arbitrary smooth map, remember, from here to here, this Jacobian. And here we have its adjoint. And this diagram commutes. You go around, you get the same thing. That corresponds to this intertwining, or is implied by the intertwining. And what I'm going to talk about depends on really probably three rather simple observations. One is the existence of a horizontal lifting map up here. So HU, the horizontal lift, which goes from EPU, its linear map, to RK. And it's a unique map, I'll call it subscript U, which makes this diagram commute, so that if you go along here, it's the same as going along here. And the definition, therefore, has to be, you take something here, look at some inverse image, and just take it round and get what it is. And the whole point is it doesn't depend on the inverse image, and that's because of the semi-ellipticity, positive semi-definiteness of the symbols. It wouldn't work without the positive semi-definiteness. So that's this horizontal lift. What I want to do in order to get further, because I want everything to be smooth, is to assume that A is cohesive. This would be implied by ellipticity of A, but it means that sigma AX has constant rank. So in other words, E of X has constant dimension. So that's for all X, Q say. And secondly, we don't want the drift term to stick out of this. So there are various ways of doing this. We want, if A, given this, we can always write A in Hofmann form. So perhaps I better do that over here. So suppose A is sigma over J, xj. This will be J equals 1 to some number we haven't used so far, M, let's say, plus x naught. So the xj's here will go from Rn to Rn in the vector fields, smooth vector fields. Then cohesiveness implies that xj of x belongs to Ex for all x in Rn. So somehow or other, everything is happening in this subspace.
And x naught.
And x naught. Yeah, that's the main point. J equals naught up to m. A consequence of this part is that H, this horizontal lift, is smooth in U. U's up here. So a lot of what I could say would be all right without assuming this extra bit, but I'm going to definitely assume that x naught lies inside here. Otherwise I wouldn't be able to do the next sort of constructions. So now I can construct some horizontal lifts of vector fields. Just making this. So first of all, suppose A is a vector field on Rn, and now I have to assume that A of x belongs to E of x, all x. Then we can define AH, which is going to go from RK to RK upstairs by AH at U is just equal to H of U, A P of U. So I've taken a vector field on my down here and lifted it up to there. H being smooth will mean that the lift is smooth provided A is smooth. So I think of one space here and one space there, and I just lift this up. And in particular, I can do this if I choose a Hofmann form to these vector fields here. So that means I can construct A of H by saying this is a half sigma over J, the horizontal lift of these vector fields. So I couldn't do that unless x naught also took values in Ex. So that's our horizontal lift of the diffusion operator. And then the main result, initial result, is that we just have a decomposition. So that we can write B is A of H plus BV. Where this one here is vertical and this one is in some sense horizontal, it lies over A. So this is it's a horizontal and vertical decomposition. It's canonical in the sense that this decomposition is unique. It's unique if we require that AH is cohesive and not at all vertical, whatever that means. But one can make good sense of it. So there's a unique decomposition of B into something which is cohesive, not at all vertical, and something which is vertical. The differentiation only takes place in the vertical directions. By vertical, I mean in this map from Rk down to Rn. Okay, so that's one setup. If you're getting a bit more close to what was suggested, that filtering is more concerned with SDEs, let me look at the situation for SDEs. Suppose that A and B now are given by stochastic differential equations. So A will be given by one which I'll write little dxt is xxt, eta, dbt plus axt dt, and the one upstairs, dut, I'll put tildes on. And initially I'll allow a different noise upstairs. So here, for example, x at x is for each x is a linear map from Rm to Rn, and B is a Brownian motion on Rm. So in the Hofmann form representation for A, we would have xjx would be equal to xx. Ej, where Ej is a basis for Rm. So that's a relationship. Of course, giving an SDE is the same as giving a Hofmann form representation. And, of course, x tilde at u, I'll take a difference. And B is a Brownian motion. B tilde is a Brownian motion on R K on Rm tilde. So generally I'm thinking of M and M tilde being rather bigger than n and k, but it's not necessarily so. So this means, for example, that sigma a at x has been factorized into x composed with x star. In particular, I want to record these xx of Rm is equal to our sort of admissible directions, Ex. And I'll need to use the inverse of x, so I'll set Yx equal to x restricted to Ex, sorry, xx inverse, considered as a map from Ex to Rm. It's a pseudo-inverse, of course. And then the formula I want is xx, yx is the identity from Ex to Ex, and that Yx, xx, is a map from Rm to Rm is equal to the projection, which I'll also call k perp x, from Rm to the kernel of x of x, perpendicular. So what this is doing, this projection, this is where my Brownian motion lives. It's projecting away from all the stuff which is redundant in the Brownian motion. So I could equally well put a k perp x here if I wanted to. It wouldn't change anything, because all this stuff, I'm assuming there's a big kernel here. But okay so far. So now I'll go to hopefully I'll go to this, but maybe I won't. So now I want to go see what the lift looks like for the stochastic differential equations. And in this situation, I claim there's a unique lift. This is about the second simple observation. There's an easy lift from Rm to Rm tilde, taking one noise to the other noise, which makes all these arrows commute, and whose kernel is the same as the kernel of this. It's an easy immediate consequence that the horizontal lift is given in terms of these stochastic differential equations by this formula here, by the LU and those. So it's a sort of concrete formula. That's the reason why I wanted to record what these things were. So for example, if we want to look at the horizontal lift of our stochastic differential equation, all we have to do is to look at the equation up there. I've just lifted everything using this same construction as I did for lifting the vector fields. Because I've written things in Ito form, I get a Stratonovich term, because I have to be careful. If I had written it Stratonovichly, that wouldn't exist. And I have a formula for the diffusion coefficient of the lifted one. It's just got, it's the horizontal lift of the x, but now we know what the horizontal lift of the horizontal lift map is from the last three in terms of x tildes and y, and so we get the horizontal lift of x is given by this formula here. And you apply it to E, it's got by actually killing off the redundant noise and then lifting it up. So this will be, I'll come to something which, so perhaps even closer to the filtering situation is where the M and the M tilde are the same, where we have the same noise upstairs as we have downstairs. So this is when the picture collapses, when they're p-related, when the vector fields upstairs map down to the vector fields downstairs. And that's the picture here. And now our LU has a very simple form. This is just the automorphism of Rm. It's just given by this projection onto the orthogonal complement of the kernel of big X. So it really is just killing off the redundant noise. So it's very concrete. Now, the other simple observation came a long time ago with Mark Yore, where we examined this notation of redundant and essential noise. So assuming we have an SDE like this, with a M which is larger than the N, there are a family of orthogonal transformations of the space in which the noise is. So OM, the orthogonal group of that, depending on time and depending on the path, the solution X, mapping the kernel to the kernel of big X, and so therefore mapping its orthogonal complement to itself, such that if we make the definitions of BE for essential noise, means you first of all, well, let me look at the redundant. Beta will be the redundant noise, which means you project the K onto the kernel of big X. This is the stuff which doesn't have any effect in the SDE, and pull it back by this translation map, these orthogonal transformations, that we'll call redundant, and then the other bit will be the essential, where we project onto the orthogonal complement. And it turns out that these are independent. That's pretty obvious. Obvious, in fact. There are Brownian motions on the kernel at our base point x0, and that should be an x0 here. And the filtration of X is the same as the filtration of this Brownian motion, BE. That's an important point. That's perhaps slightly less obvious. Here's a repeat of the definition, from which is, I just want to make the point that we have actually decomposed our Brownian motion using an Ito type decomposition into redundant and essential noise. So now we can decompose our SDE. I'm assuming we are in the p-related case, so our m's and b tildes are the same as b. So this is the stochastic differential equation upstairs. We can substitute for dBt as the sum of the essential plus the redundant. So I've just done that on the top line. We can rewrite it, if we wish, in terms of horizontal lifts. And so we have gone down, let's go down to the bottom line now. So we've got xh dBt plus ah dt. So that's basically the lifted stochastic differential equation plus other stuff. This is not, again, horizontal because it's Ito, and so there should have to be some stretch terms. So it's not a perfect decomposition in the Ito case, but it's still adequately useful. And the other stuff should be vertical. But in the Stratonovich case, it's clearer. We can write, we just substitute for dBt, but we have problems. We have to be careful about, we can't use the essential noise without changing to Ito equations. So here I've just written our Stratonovich equation as a horizontal bit plus another bit. So this will be the generator of AH, and that will be the generator of BV. Sorry, the other way around. This will be generated by AH, and that will be generated by BV in our decomposition of the diffusions. So now if we proceed a little bit from the last one, we had a term which was a horizontal lift of dxt, in fact. So I've just rewritten the equation from the last slide, basically in a slightly different form. And I've rewritten some of the vertical stuff in terms of the redundant noise. So if we have a function f from Rk to R, we can write f using Ito's formula. I've just written it here. We get f of ut is something, the blue stuff depends only on x, and this stuff depends on the vertical operator and redundant noise. So this is now, if you want to do some filtering in the usual sense and condition on x, it's when you condition, you'll just get rid of the beta. So this is to tie in with the usual notation for f, moderately usual notation. If we define pi tf as a conditional expectation of a function of ut given xs, so I'm looking at functions up here, given the behavior of p of it, then I immediately get this, which is like one of the formulae which was written up this morning. It's essentially that formula. Zakai's equation. Yeah. But, of course, what I've been assuming is that our projection is Markovian. But before I want to go into that, I would like to say that there's another decomposition of our operators. I claimed that the decomposition we had there was unique, assuming AH is cohesive and not at all vertical. But if we started with SDEs, as you might in a filtering problem, they determine Hilbert spaces of vector fields. I mean, finite dimensional if we only have m of them, just the things spanned by these xi's. The noise part I'm only interested in. So h tilde spanned by the x tilde i's, and h by the xi's. We have a map p star which goes from one to the other, as shown up there. We let HH perp be the kernel of this map. And then again, we get H tilde, the space of vector fields, giving the noise, is the direct sum of HH and HH perp. We can take orthonormal bases for this and orthonormal bases for that, write down the Hormander form operator. I think I'm assuming there are no x naughts for the moment, for simplicity. And we get that B is the sum of two diffusion operators, one of which is certainly vertical. The other lies over A, but this is generally different because the vector fields which determine this all project down to 0, are the only ones which project down to 0. So this does not satisfy that it's not at all vertical. So this is actually a different decomposition. rather than, and it depends on choosing an SDE first. So it's not, in that sense, canonical. Okay, so just in case you're not sure how this can fit in with classical filtering, in the classical filtering situation, with, I'm afraid, a different notation from normal, you would have a signal process, which I've written here as dzt, an observation process, xt, and what you did, as Professor Krylov did, you can take ut to be the pair of them. So to fit in with what I've been doing before, Rk is the product of the two. And we have and Rn will be the projection down to there. And then we're in a more standard situation. The only standard situation is that normally that you have this situation here which doesn't fit in with what we were doing because we assumed that our x was Markovian. But again, this is a normal practice in filtering, is to remove this by use of Casanov's theorem. I'm assuming everything exists for all time and everything's cohesive, so you can certainly use Casanov's theorem. So then you change probability, use the usual business. So now I'd like to look and see how this works out, a few examples. So first of all, a rather artificial SPD example, and then if I have time, something about flows and something about gradient estimates, which is where it really came from. So let's suppose we have an SPDE. So here I'm going to allow my spaces to be infinite dimensional, this big space. And I'll consider the second example. Suppose we have one obvious question with an SPDE might be how to, if you know the 1-point motion of a solution, how can you estimate the full lot? Rather easier in the one I'll do will be if you know the integral of the solution. So I'm assuming that this will be given. So I'm going to take a very simple example. So I'll take the space will be a circle, and I'm going to consider about the simplest one I could think of for an SPDE, where you have a Laplacian on the circle, so it's one-dimensional space, a noise WT and a BT. These are just one-dimensional Brownian motions. And our observation will be this integral. So our dxt by Ito's formula will just be given by this. So it's already a martingale. We don't have to do any changes of probability. M is just a constant, not 0. So we can consider ut in some Sobolev space, and so our mapping now is from Rk is now replaced by the Sobolev space, and we're mapping down to R. So what I'll do is we can calculate the horizontal lift map, just written in terms of u. Pu is the integral of u, a very simple formula. We'll recall we'll look at it in two ways. One by looking at the Sakai formula, and we'll suppose that we're taking f to be a valuation at z. This is the thing we're going to estimate. So what we obtain from this is a typical SPDE, or the sort of thing that people who do filtering are very used to and can curl their lips up and do in their heads. But actually they wouldn't have done it to start with, I think. Because if you did the decomposition method, which is a slight variation, we could write dut, which was a stochastic differential equation, into its horizontal and vertical parts. And this corresponds to some of the slides I wrote before. So here we have this rather complicated bit left over. The first part is a sort of horizontal lift of x, and then there's this junk here. But this junk is actually independent of x. So when we condition, we just get that the conditional expectation satisfies that. So this gives out a very simple, straightforward way of calculating the conditional expectation. I mean, we can solve this equation now. It's just a simple linear equation. Of course, you could have done that by taking Fourier, doing Fourier analysis right at the very beginning. But still. So that was the reason I gave that was an example where the decomposition method works very easily, and it's rather easier than going to the Zakai equation. Let me go on now to look at something we did earlier, which was one of the more motivations. So now we have a slightly more complicated space. I'll take M to be a compact manifold, so Rn is now replaced by something which is easier to deal with, because by the compactness. So my big space at the top is going to be the diffeomorphisms, smooth diffeomorphisms of M, or HS diffeomorphisms. And I have an SDE on my manifold here, which I'll assume cohesive. So the generator of this will be my curly A. And I have a stochastic flow of this differential equation. So the stochastic flow consists of diffeomorphisms. So it's actually a process on diff M. Using our decomposition, what you get out of it is a skew product decomposition of the flow into a horizontal lift of the one-point motion. I never said what P was. So P in this case, diff M to M, is given by theta goes to the evaluation of theta at x naught. I fix a point x naught. So x is a one-point motion. So my flow, from what I've been saying just now, that the flow gets a skew product decomposition into something which depends only on the one-point motion, that's the x tilde t, and the other one is vertical. It consists of, it's independent for each sigma, it's driven by an independent noise. So it's a genuine skew product decomposition. So, for example, if you really believe that stochastic flows could model oil movements, you would reckon that this way, if you know the movement of one particle, you could get information about the whole lot. Now, the construction of x tilde is very pretty, which is really why. X tilde is a solution flow to a very simple SDE on M itself. So that decomposition is quite simple. Finally, one of the original, well, I won't give there's a precise formula for the vertical part of the skew product decomposition, which I won't, not very, whoops, that's not it. No. So finally, I'd like to mention what was a sort of standard application of some of these things was, suppose you have perhaps the situation I had just now where you have a flow, or SDE on something. So you look at its semigroup, PTF, for functions on M, and you want to work out what the derivative of the semigroup is. So you do what you want to do, you differentiate under the expectation sign, and this is if all's well, in the compact situation, you get a formula for the derivative of the semigroup and can perhaps get a gradient estimate. On the other hand, you can do a little bit better by using the sort of techniques I mentioned, because you can then rewrite in here the conditional expectation of this derivative given x. This is something to do with the flow. In general, it involves a lot more noise. So that this actually, and in geometrical situations, this will usually belong to some sort of curvature. So it gives you a better estimate than going directly to that. So this is got by filtering out the redundant noise from your stochastic differential equation. So thank you very much. Oh, well, no.
If you can know a few linear functionals from U, which contains more information about solutions, so what's better to know, integral or varying the point?
If you know, sorry.
If you can know only a few linear functionals of a solution, which contains more information about the system, what is better, to know the integral or to know at varying the point?
Oh, I see. Well, I guess the integral. Well, in that simple example, because you can get everything.
How to formalize this statement? What is which sense the integral is better?
Well, okay, yeah. So perhaps I'm jumping.
The question is how to formalize the question.
Yeah, that's what you say.
Okay,
The structure of nonlinear problem is you have a function of observation.
So it's much easier to deal with whether you get something which is a closer approximation by doing this than by trying to get the function of the. I don't know. But the easy way to get all information is by actually doing the filtering for all the Fourier modes, which comes out the same way. I mean, in this particular example.
Other questions?
I mean, your starting point is something which makes sense in a Markovian setting. You've got a Markov process upstairs, you project it down, and it has the remarkable property that it's still a Markov process. And indeed, the dynamics of that process are independent of where you started on the fibre above the point you start at. So it suggests to me that there must be some sort of Markovian story here that requires no diffusion assumptions, that it should be possible to tell a story where you observe the path of the projecting process and you can work out, because you well identify this property that when you look locally in the big space upstairs, when you look locally in there, the sort of the horizontal component is doing its thing, and then the vertical component is more or less independently acting. Now, of course, the dynamics of the vertical component may depend on where in the vertical fibre you are, and also where you are downstairs. So there's a lot of richness that's possible in there. But I mean, if you think in a sort of discrete example for a moment, where you maybe have sort of discrete values of the state space and discrete time, then you start off at some point, you have a prior distribution of where you are in the fibre above, and then you observe that you jump to another point. Well, what you've got then is you've got, as it were, the sort of kind of the composition of or the convolution, if you like, of where you started with the one-step transition probabilities from there. So it might even be possible to kind of describe the entire evolution of the conditional distribution in a deterministic way, given that you've observed the definite path downstairs.
In a more general setup.
Yeah, in some sense, yeah.
I hadn't thought about more general situations except to ask people whether they could do it for Levy processes in which they almost claim they can't.
Well, I
But,
think it will be very confusing. Yeah, I mean, theoretically, there's very little that you can do. You can write down formulae, but actually to kind of crank out numbers, game altogether. But I mean, if you discretize everything, if you're going to crank out numbers, of course you've got to discretize everything. If you pose the question in discrete time, discrete state space, then I believe there's a lot that you could actually do. But well, we can talk about that.
Other questions? Thank you very much.